Our next problem is particle in infinitely depth potential. Well, first we have to write a one-dimensional Schrodinger's equation that we have already known. That is the a d2 psi by a dx square plus a 2m by h bar square e minus v psi is equal to 0. Say we call as equation 1. So this is the one dimensional Schrodinger's steady state equation. d2 psi by dx square plus 2m by h bar square e minus v psi is equal to 0. Okay, and we are applying this equation for a particle in infinitely depth potential one. So first we have to see what is a symbolical diagram for one dimensional potential valve, and that is the depth of that potential valve is infinite. See, if your particle is going along the x direction, in x positive direction, and then the potential in between these two is like this. And when particle is at x equal to 0, then this is a boundary of the potential, and there is another boundary of the potential x equal to a. There is another boundary at x equal to a. So there are the two boundaries. One is at x equal to 0 and another is at x equal to a. So we divide these diagram into three regions. One is a region first, then a region second, and a region third. Okay, and according to the infinitely depth potential, this diagram is again what is the potential at region first, second, and third, and this a potential at first region is infinite. Region second, a v equal to 0, and region third again a v is equal to infinity. Means our problem, our particle is moving, confined to move between x equal to 0 to the x equal to a. So this is our the motion of the particle in between x equal to 0 to the x equal to a. Means that motion is constrained by applying this voltage, applying this potential between x equal to 0 and x equal to a. So we solve this Schrodinger's equation for this region second, and therefore if we put this value of the v equal to 0 in this equation, we have then this equation first becomes a d2 psi by a dx square plus 2m by h bar square v equal to 0. So this v equal to 0 means this e psi is equal to 0. Put this 2me by h bar square is equal to k square, and we have so this a d2 psi by a dx square plus k square psi is equal to 0. Say equation 2. Now to solve this a particle in infinitely depth potential valve using this equation d2 psi by dx square plus 2m by h bar square e minus v psi is equal to 0 means to do what? So there are the two exercises. One, to find out the eigenvalue E. We have to find out E is eigenvalue. And another problem, and there is another exercise to find out a psi n eigenfunction. So to find out, to solve this problem is nothing but to find out the En eigenvalue, and another exercise is for the eigenfunction. And lastly we see the diagrammatical representation of psi n and its probability distributions. Okay, so first we have to solve this equation for eigenvalue, that is the psi n, and we continue forward. Uh, so this is the differential equation, and solution of this differential equation is equation 3, where a and b are a constants, and these constants can be calculated. This constant can be found using the boundary conditions. So first boundary condition, at x equal to 0, so this psi x is equal to 0, and therefore put these boundary conditions in equation 3. We have a 0 is equal to psi of xt is equal to 0. This a is sine kx x equal to 0 multiplied by 0 means it is sine 0 plus b cos 0. B a cos 0, b cos 0, and therefore this 0 is equal to a sin 0 plus b cos 0. Sin 0 0, cos 0 is equal to 1, and therefore 0 is equal to b. That means the value of the b is equal to 0 using the boundary conditions. Put this value of b in here in equation 3. We have this a psi of xt is equal to a sin kx. Psi of xt, a sin kx is equal to equation 4. Now there is a is nothing but your normalization constant. Now is equal to 0. Is equal to 0. Now at x equal to a, there is another at x equal to a, we have a psi of xt is equal to 0, and therefore this equation becomes 0 is equal to a sin ka is equal to 0. Okay, therefore this is sin into a, k is equal to 0, means either a equal to 0 or sin k is equal to 0. But according to the probability of the finding the particle in between x equal to 0 and x equal to a inside the box, inside this region second, is not equal to 0, and therefore probability of the finding the particle outside this region in first region and second region is 0. Therefore this a not equal to 0. If a is not equal to 0, then a sin ka is equal to 0. Okay, if the sin ka is equal to 0, so therefore the value of the ka is equal to n part. The value of the ka is nothing but the n part. Okay, so therefore this ka is equal to, here we write here, this ka is equal to n part, and value of the k is equal to this n part divided by a. N part divided by a. Take the square of this. So this k square is equal to n square pi square a square. N square pi square a square, and we know that the value of the k square is equal to 2ne divided by h bar square. And therefore we know the k square is equal to this 2m e divided by h bar square. So these two are equal, and therefore solve for e, and we know that this e is equal to n square pi square h bar square divided by this 2m a square, and therefore This En, we write it is an En because here it is n. Why it is n? Pi square is a constant. H bar square is constant, h upon 2 pi. 2 is constant, m is the mass of the corresponding particle, and a is the width of the valve, which is also constant for this problem. And therefore, En is equal to n square pi square h bar square divided by 2ma square. So all this is the constant, means the En is directly proportional to n square. En is directly proportional to the n square. Okay. Now first calculate energy value, the lowest energy value, by putting n is equal to 1. So this is called the lowest energy value, and this E1 is equal to, put n here 1. So this becomes pi square h bar square divided by 2ma square is E1 is energy value for a lowest energy value. For E2, so this E2 is equal to, n is equal to 2. N is equal to, E2 is equal to this 4 pi square h bar square divided by 2ma square. But what is this? This is nothing but again our the E1, and therefore E2 is equal to a 4E1. E2 is equal to a 4E1. Now E3 is equal to, put n is equal to 3, and this E3 is equal to 9 n square h bar square upon 2ma square is equal to 9E1. 9E1. Like that we can find out the value. En is equal to, so this is the n, so this is 3 9 square 2 4 means n square. So this is the n square E1. This is the n square E1. So E1 is equal to n square pi square h bar square upon 2ma square is the energy E1. E2 is equal to what? E2 is equal to 4E1. E3 is equal to 9E1. And therefore, if you draw the diagram for energy level is, so n is equal to 1. So this is the lowest energy E1. Then n is equal to 2. So this is a 4E1. N is equal to 3. This is a 9E1. Is a 9E1. So this is the energy diagram. And n is equal to 0 means this is the ground state energy. 0 energy level. Okay. So there is another problem. Find out this wave function sin x. Last time we see the energy eigenvalue. Now the eigenfunction. What is the eigenfunction for? We have, so this sin of xt is equal to a sin k. Value of the k is, so this is the n pi by a x. N pi by a x. Okay. So this sin n pi by x a is equal to a is normalizing constant sin n pi by a into x. To find out a value of this a normalizing constant using normalizing conditions, and therefore we know that the integration is a mod of square is a sin square of n pi by a x dx is equal to 1 according to a condition of normalization, and therefore we have take outside here. So this a mod of a square, the integration sin square n pi by a x dx is equal to 1. So sin square formula is there. this is sin square theta is equal to 1 half 1 minus cos 2 theta. 1 minus cos 2 theta, and therefore put this value here. We get this a square integration this sin square theta is nothing but what, 1 half 1 minus a cos of 2 theta, means this 2n pi by a into x dx is equal to 1. 1 half take outside here, and therefore mod of a square by 2, the integration 1 minus a cos of 2n pi by a x dx. Integration of cos is sin theta by theta, and this one is a, and therefore this integration becomes, value of this integration becomes as a minus sin 2n pi by ax divided by this 2n pi by a 0 to a. When we are putting this value of 0 minus this value of a, then we get this mod of a by 2 into bracket this a minus sin 2 pi n, and this value of the sin 2 pi n is 0, and therefore is equal to 1, this is, and therefore this a square by 2a is equal to 1, and therefore a is equal to root 2 by a. This is the value of normalization constant. Put this value of normalization constant in this equation, and therefore the wave function sin xt is equal to a, and a is equal to root 2 by a sin n pi by a x. So this is your wave function, but eigen function. This is called the eigen function. So there are the two exercise. One is to find out eigen value, and another is to find out the eigen function. Okay, जैसे कि हमने एनर्जी के बारे में जैसे किया था, the same we are going to find out for the eigen function. So that is the psi 1, psi 2, psi 3, like that. Means this is psi n of x root 2 by a sin n pi by ax is a wave function. Corresponding energy, eigen energy is en, and therefore now put the n is equal to 1. We have a psi 1 of xt is equal to root 2 by a sin. So this is the nothing but this pi by a into x. So this is the same. Corresponding eigen energy is E1. So this is the pi square h bar square upon 2m a square. Okay, so corresponding energy. Put n is equal to 2. Psi 2 of x is equal to 2 by a sin 2 pi by ax, and corresponding energy. So that is the corresponding energy. E2 is equal to 4E1. Like this. E2 is equal to 4E1. N is equal to 3. N is equal to 3 is equal to sin 3 of xt is equal to root 2 by a. This is sin 3 pi by ax, and E3 is value. E3 is equal to 9E1. Corresponding energy, eigenvalue energy, and therefore so these are the different states, and these are the corresponding energies. So this exercise shows that there is no continuous spectrum of energy. it has a discrete energy levels. So this diagram also same. So E1, this E2, E3. So it is not a continuous spectrum like in free particle. Okay, in free particle we have seen this is the continuous spectrum, whereas this infinitely potential well, because of these boundary conditions, when applied on this particle, then there are the discrete energy levels. Then find out this psi 1 if you plot here. So this is x equal to 0 and x equal to a, and this will becomes a psi 1. So this is the psi 1. Okay. Modulus of this one, probability density, and probability density for this we plot here. Probability density x equal to 0 and x equal to a, and this is nothing but this is the a mod of psi 1 square. So this mod of psi 1 square is a probability density. So there is a maximum probability of density is at the center. Okay. So this is for the psi 1. For psi 2, here it is. So this is the psi 2, and probability density for psi 2 is, so this is the 1 and this is the 2. So there are the two probabilities in between, and for the psi 3, you draw here like this. So this is the first, second and third one. So this is for the psi 2, this is for psi 1. So x equal to 0, x equal to a, and probability density. So probability density, so this is the first one, this is second one, this is third one. So x equal to 0 and x equal to a. So there are the three probabilities are finding here. So this is the psi 3 mod square. So there is another one. When psi 1 is there, so there are the two nodes. Psi 2 is there, then n is equal to 2, psi 2 for 1, 2 and 3. 3 nodes. Psi 3, n is equal to 3, 1, 2, 3 and 4. 4 nodes. And psi n, and therefore for the psi n is equal to n plus 1 nodes. Okay, so this is the in general formula for the psi n having and psi n is equal to n plus 1 nodes. Okay, so this is the problem for the infinitely potential well. When we applying this steady state equation for this problem, so there are the two exercises. One is to find out the eigenvalue and to find out the eigenfunction. Okay, so are you understand? So this is our the second exercise for Schrodinger's steady state equation. So first one we see a free particle, second one is this infinitely depth potential valve. Now we are going to in three-dimensional box next time. Okay.